Okay, this is part 2. I'm coming back to question number 13 because I realized I skipped it on the last video. And the answer is actually D. And my only good explanation for this one is that we're dropping the ball. It does form a periodic motion. So in other words, the ball bounces because it goes down and it comes back up and goes down and comes back up, goes down and comes back up. So it is a periodic motion, but it's really not a simple harmonic motion. And so that's the only reason why I would choose D as the correct answer. And how they got the period, I'm not exactly sure. But I ended up trying to find out what the time it would take, so relate the time back to that. And I would guess that it would have to be close to that 2.8. Anyways, that was 13. Now I want to go forward to number 18. And in 18, we have this graph that represents kinetic energy versus time. Okay, so I looked at it in terms of trying to find. Oh, here was. So I've got this graph up here, which was my position versus my time, and this is my kinetic energy versus time. So as I'm traveling along, I start at the origin, which means that I have a position here that would have a positive slope. So again, I'm remembering the fact that slope of a position time graph is velocity. So in other words, I have a great velocity here, but then up here my velocity curves down, so I get a zero velocity, which if I have zero velocity, I have zero kinetic energy. So this flat spot here represents zero kinetic energy, and this flat spot here represents zero kinetic energy. And this point here represents a maximum kinetic energy, kinetic energy, and maximum kinetic energy. Now the nice thing is you have to remember that kinetic energy is always going to be positive because it's a scalar quantity. And when I look at my graphs, I'm looking for 3 points that would represent maximum kinetic energy and 2 points that represent zero kinetic energy. So I have my 2 points with zero and my 3 points with maximum. That's how I got B. Number 19, which of the following graphs show the displacement? Okay, so again, I'm going back up here and I'm looking at this original graph here to look at what's going on with kinetic energy versus position. So again, I'm at maximum kinetic energy when I'm at 0 on my position graph, and I'm back at a maximum at 0 and a maximum at 0, and I'm at a zero kinetic energy when I'm at a maximum position. So I look at my maximum position with zero kinetic energy, and I oscillate back to this one. So that's how I kind of look at it in terms of that. I'm looking for zero position with maximum kinetic energy, or I'm looking at maximum position with zero kinetic energy. Number 20, we've got a satellite that's been traveling. So we're looking at how the speed adjusts from here, and how does the angular momentum go from there. And again, angular momentum has to be conserved. That's one of those quantities that has to be conserved. So I'm getting to the point where I'm either at A, E, D, or E, and I eliminate A immediately because the speed has to change as I start to change these directions. So again, changing my directions since I have an acceleration, and an acceleration is changing speed. So then I look at it and I narrow it down to that it's increasing. So I'm starting here and I slow, but I pick up the speed as I come around. So again, I'm increasing because I'm getting a tighter radius. Number 21, we have our planet here that we are looking at. So in other words, I did a universal gravitation equation, and I eliminated the fact that the G in the, hold on, so this was my radius of my Earth, and then the next one I doubled it, and so then I my mass of my Earth remains the same, and I compared the mass of Cosmos, which was 4 times greater than the mass of the Earth. So I have mass of the Earth is equal to 4 mass of the Earth divided by my radius of the Earth, and then I looked at the new radius, or what the radius of Cosmos would be. So then I reduce this down to the point to where I'm down to r squared is equal to, and I brought this one over here, so I did a little cross multiplying. The g's cancel because they're the universal gravitational constant, and the one of my ME's cancel because of that same reason that I've got them there. So I got that is equal to 4 times that, and so that cancels out both of the ME's, and then I just took the square root of that and got 2 and RE, so that's how I got my answer. Number 22, we have our artificial satellites. They were heavy on satellites and rotation stuff here. We're looking at the acceleration as we go from these 2 different points when we increase our radius. Trying to see where's my work for this one. I think this is my work down here for it. So I've got my F is is equal to the G MEM R squared, where my R1 squared is this, and then I said, well, what happens if I increase this? Oh, I said that's equal to my net force. My net force was M is A1, and so now I got A1 is equal to this quantity. And then I said, well, let's make A2 is equal to a similar quantity. And now all of a sudden these 2 quantities are relative to or proportional to each other. And so that I could then see that A was equal to, because if I square that I got 4R1 squared, and I did a substitution someplace here to get A1 is equal to 4A2. Okay. Number 24. With the ball, and we're looking at 2 positions as it's being released. Oh, we have maximum potential energy up here, we have maximum kinetic energy down here, and we get back to maximum potential energy up there. And so I set this up as a kinetic energy problem, and I looked at it in terms of we're looking at the acceleration. That's what we're doing. The acceleration vectors. So in other words, at these points, at my maximum potential energy, my acceleration is acting downward. So I have a downward one here, which is going to cause it. At this one here, I'm actually at my maximum kinetic energy, which means I'm looking at it in terms of the acceleration I see is centripetal. So the centripetal is up. So I get upward here, and I get downward over here. The bowling, 23, I think I skipped that one. The bowling ball has a mass of that, and we have our moment of inertia. And so I looked at this in terms of the kinetic energy is equal to the potential energy. Well, the kinetic energy has 2 parts to it. There's the translational kinetic energy, so based on that velocity, and then there's a rotational kinetic energy, which is due to that moment of inertia. And that was going to be equal to my mgh, okay, or my mass graph times gravity times the height, and we were looking for the height, I believe. The nice thing is that once I did some substituting and I figured out my moment of inertia was this, so I plugged that value in, and I know that the omega squared, or my angular velocity, was equal to v over r. And so then I plugged those in, squared it, and I got a lot of stuff to cancel, and I got down to this point where I could then get my answer. 25, we have an object moving on a curved path, and we're looking for the vectors that would represent its force, velocity, and its acceleration. I did some process of eliminations with these, and I looked at them and said, no, the force, or I should say the velocity, has to be acting in a direction that's along or tangent to the curve. And so that's how I eliminated A and B from this. And so I got down to the ones that were just there. Then I also looked at it and said that I have to have my force in the same direction as my acceleration, because I believe that they were asking for a net force on this one. And so that's how I eliminated C. And then I looked at it and I said, oh, C and E, and then I saw it brought me to D, and that made the most sense because my acceleration should be acting kind of at a direction somewhat along the line. So number 26, we've got the particle moving in a circular motion. And so they gave me the two functions, the x function and the y function, with respect to t. I did derivatives of both of those, and that gave me velocity functions in the x and velocity function in the y. And so it was kind of a chain rule for my doing my derivatives. So that would be the one harder calc problem. So, but they do have that on the sheets. They'll give you those trig functions, the derivatives of those. But that's how I got to the 15. So y was always equal to 15. And essentially, as one is increasing, the other one's decreasing, but you're always going to be at 15 in that loop. So that's how I got a B for 27. For 26, we were looking for the period of the revolution, and the period is going to be 2 pi, so what value do I have to plug into my function here to get 2 pi? And so that's where I got the 2 pi over 3, because when I take that times t, I get then 2 pi, and that gives me my period. 28, we've got two objects, they're sliding into each other, and so I did free body diagrams for each of the two objects, and then just looked at how I could solve for that, and that's how I got to 8 newtons. So that one was a kind of a straightforward free body diagram problem. Number 29, and actually I'll probably pause here so that I'll do 29 through 35 on a last video.